privileged to introduce you to Dr. Francisco J. Reyes. He is assistant professor of the Department of Astronomy in Chile. He's also director of University of Florida Radio Astronomy back in 2000 to 2010. He's associate scientist with the Department of Astronomy at University of Florida currently. He got his PhD there in 1989 and his MS in 1980. He's also got his electrical engineering degree in Chile in 1977. And he's had a lot of experience with different aspects of radio astronomy. A lot of it is related to the research on the emissions from planet Jupiter. And what struck my fancy there is I know that that's one that you can kind of pick up with regular ham radio equipment. So it's a good way to get a first taste of what's up there in the sky in the radio astronomy, in my opinion. Let's see, what else can I say? There's lots of things here. In 1974, he joined a group at the University of Chile, Maipu, I hope I'm pronouncing that right, Radio Observatory, and got involved in the design, construction, adjusting, testing, and calibration of a 528 full wavelength dipoles array at 45 megahertz. So that's a pretty large antenna. He graduated the school at the University of Chile, the School of Engineering, as I mentioned, as electrical engineer. And his thesis was radio telescope at 45 megahertz for galactic and extragalactic sources. Later on, he went to the University of Florida, got his master's and PhD. His dissertation was, for his PhD, was observation of pulsars at low frequency. And he did those pulsar observations using the 26.3 megahertz, right above the 15-meter ham band, 640 dipole large array in Florida, which I've driven by there before. A lot of people might not know that's here. It's not operational now, but Dr. Reyes can fill you in on the details of it. So he also has many interests and hobbies, including photography and astronomical photography, teaching astronomy, which is perfectly suited to why we like having him here tonight. And then, of course, he's a radio amateur. And I forgot your call sign there. I didn't write it down. Oh, there it is. KK4 Alpha Alpha Victor. So, Dr. Reyes, I appreciate you coming tonight, and thank you very much. And I'll turn it over to you. We can possibly post some questions on the side, or just wait later and ask at an intermission or at the end, however you wish to do it. So, Dr. Reyes, thank you.
Thank you. Thanks for the for the introduction. So yeah, I began as an electrical engineer, but very interested in astronomy. So there was a way in which I could connect with radio astronomy, and that was very interesting because that took me in a different direction. And I finally began being a radio astronomer and finally an astronomer. So, but my interest in electrical engineering still continues. So I'll probably tell you a few things that I have been doing. So let's see if I can share the screen, and let me see if you allow me to share the screen here. And let's see if I can.
It looks. We see your presentation.
Yeah.
Can you see that one? Let me go to the full screen there. Right there. So everybody can see that?
It's perfect.
Yeah, okay. So I'm going to concentrate pretty much in low frequency radio astronomy, and that is what I have been doing. And you will probably see how many megahertz are going up, but not too many. So that's pretty much my field there. So right now, I'm an associate scientist here, and I'm teaching astronomy class. I'm the director of the observatory. We have one here on campus, another one near Bronson. And I'm in charge of telescope and instrument and everything that had to do with that. I think they took advantage that I have some kind of interest in engineering, so they gave me a lot of things to do here. So let's start talking about what it used to be the University of Florida Radio Observatory. And so here you have part of the story. I can tell you from the beginning that we had to stop operating the radio observatory, and that was a pretty sad thing that happened because we normally had one person there, which was the permanent observer, and that person left. And then after that, a few years, they began destroying part of the antennas there, and that was pretty sad. We tried to repair some of the things. Well, within a few weeks, they came and took more part of the things there, part of the antennas to sell them as aluminum. They took part of the coaxial cable to sell them there. So probably they got $20 or $30 out of part there for something that cost probably several $100,000 or so. So we had to stop finally that. So let me tell you a little bit part of the story here. The program here was started around 1957. And the main topic there for the research was observing the decametric emission from Jupiter. That's emission below 39 megahertz. That was discovered in 1955 by Burke and Franklin using an antenna around 22 megahertz. They were having a big array there near Washington, DC. And so the things began here around 1957, small radio observatory on campus. They have just a couple of antennas, 18 megahertz antenna and an array of 8 dipoles at 18 megahertz. They had to move that one to Vivens Arm. Vivens Arm is a lake that is probably 3 or 4 miles south of here. And they moved there and the space was much bigger there. So they began building more antennas there. So I listed here, they have Yagi's antennas at 18, 20, 22, and 27. They have a corner reflector, I believe it was for 18 megahertz. And they have a polarimeter antenna. I'm going to show you some of that. Finally, around 1966, they moved to Dixie County near Old Town. It's probably about 8 miles from Old Town towards Suwannee. And that's an even bigger site. It has about 60 acres site. And they were be able to put more antennas there. So they moved all the Yagis there. They included a 15 megahertz Yagi. They built a big array, 640 dipoles. I think I have the problem here is 26.3 megahertz. That was finished around 1970. They have a 18 megahertz polarimeter. And also, I was part of the team there building an array of 16 conical log spiral. They are normally called TP because of the shape. And they are polarized. One of them, a group of them, 8 of them are right-hand polarized. The other one, 8 of them are left-hand polarized. So we finished building that in around 1995. We have them ready for the collision of the comet, which was another interesting part of the story. So here you have the people who started the research project in 1957 or so. That was Tom Carr, which was my advisor here for my PhD and my master's degree. Alex Smith, which was in charge of the radio observatory when they began there. So both of them started with the Jupiter observing program. Actually, Tom Carr was a student of Alex Smith, but then Tom Carr took over and he began the director of the Radio Observatory. Here you have a picture of some of the console when they started with that. So you saw a few things here. Let me move some of the things. Here is when they were in Bevan's arm, and you can see some of the receiver there. Some of you may remember the Collins, the 75S1 here, Texas recorder, chart recorders, and things like that. This, I think, was the first console that I had to observe. And you can see a couple of Ali Crafter receiver. You have a brush recorder and another recorder, Sterling Anguish, they call it, because they had problem with the ink that they had to unclog the things there most of the time. And here you have part of the antenna. So that is in Viven's arm. So here on the left, you have a corner reflector. I believe that was for 18 megahertz. You have a polarimeter antenna also for 18 megahertz and a Yagi. Here you have a better view from the Yagi. So it was pretty close to the lake there. And I think they had to fight with the alligators during the night when they were trying to point the antenna to Jupiter. That's what I remember people told me there, that they had to be careful with the alligators, make sure they didn't step in one of the alligators there. All right, so finally they moved to Dixie County in 1966. So here you have part of the people that were involved with that. Tom Carr was in charge of the observatory there. Carl Olson just graduated there and he was hired for the department. Wes Greenman was the engineer for the observatory, and Alex Smith was the actual director of the observatory there. So those are the people who started the things there in Dixie County. Here you can see part of the antenna. So the antennas that they have there were a row of Yagis. The first one here is 27 megahertz. The other one is 22 megahertz, 20, 18, and probably you may not be able to see 15 megahertz there. The 27 megahertz antenna was probably the one that had more elements. They have 5 elements. The 15 megahertz only have 3 elements there: reflector, and director, and the dipole. And here you can see the polarimeter, which was mounted there. Here they are trying to point the polarimeter to Jupiter during the night. And so finally, in 1993 to 95, we built the Conical Log Spiral, which are normally called TP. I think this antenna is called TP in many places because of the shape like an Indian teepee. And you can see here, the one on the left, those are right-hand polarized, and the one on the right are left-hand polarized there. For the collision of the comet, we use only 4 of them, but in the coming years, we build more of them. And so the gain of each element is not too big. So in general, for one of the 8 elements there, the gain is about 13 dB respect to an isotropic source. And here you have the big array. That was a project by Tom Carr. He wanted to build a big array to have the highest sensitivity for observing Jupiter at 26.3 megahertz. I came to Florida when the array was already working. So I actually began using the array, but I had to help with the team there. Every year we had to do repairs there after the lighting season. in which we had a lot of damage because of lightning. We had to repair and replace some of the lines and some of the network there and many other things until we make it work, and then began the next season, which normally began around September until May the next year or so. So 640 dipoles, pretty big array there. Here you can see the console that we have at the Radio Observatory in DC County. So you can see me here a little bit younger, and Wes Greenman, which was the engineer. We were the last two people that continued using the observatory there for many years until we had to shut it down. And normally we went there together to do the observations. I wrote a program that actually can do the observation automatically there. And so during the week, we were not there except when there was a prediction for what we call Jupiter storm. So we went there and recorded part of the things in magnetic tape and then played them back here. So you can see part of the things. I'm looking there to the computer, which had all the displays from all the channels that we are digitizing. You have the spectrograph here, and we were not using the chart recorders anymore, just part of the receiver that you can see there and the computer. The computer actually was doing something very interesting because it can observe during the time in which Jupiter was within the beam of the antenna, and then stop the observation and continue the next day at the time in which Jupiter began entering the beam of the antenna. It did calibrations, saved the data, and all the same. All right, so let's tell me a little bit about the science program there. So the Jupiter emission, the decametric emission, can be observed below 39 megahertz, between 1 or 2 megahertz, whatever the ionosphere allows you to pass part of the radiation, which can be around 3 or 4 megahertz, sometimes 5 megahertz, with a lot of interference, up to 39 megahertz. That's the maximum there. And the mechanism that produced the emission is the so-called cyclotron maser instability. So here you have the equation. So if you enter here the value of the magnetic field in Jupiter and you multiply it times 2.8, you get the maximum frequency. Normally the magnetic field in Jupiter is about 14 Gauss or so. So 14 times 2.8 will give you something close to 39, 40 megahertz, and that's the maximum frequency. What we were doing there is observing the emission every night. Regardless of there was a prediction or not, we were observing there. We did some kind of polarimetry there with the antennas because the emission is polarized, either right hand or left hand. And I'll show you an example of that. We did some kind of interferometry, and the interferometry was done in several places from here all the way to Chile. And then we set up another antenna here near Live Oak, and we did interferometry between Live Oak and Dixie County. And we recorded the things in magnetic tape and played them back with a 28:1 slowdown and did some high time resolution of the emission. So part of the thing that we are observing here, what is called the synoptic monitoring, was observing in all these frequencies here. And in the last 15 years, I expanded some of the things there. And so we began observing between 18 to 32 megahertz, and we recorded the right hand and left hand polarized emission. They are using the TP antennas. And what we were doing there, and we are still doing that, to construct the CML IO phase, and I'll show you that in a little bit, what we mean by CML and IO phase. is a plot that actually plot the location of the source in these two coordinates there. That is pretty much to improve the determination of the sources there, which is something that kind of very interesting to determine, and also determine the rotational period. Probably you know that Jupiter is a massive planet, but it's pretty much gas. So you cannot use any features there on the surface to determine the rotational period. But the magnetic field is tied to the core of the planet, and using the decametric emission, you can determine the rotational period of the planet. And that was pretty much the only way in which it can be done. Right now, it's been improved because they use part of the data from some of the spacecraft, like Voyagers and Galileo spacecraft. But that was the only way to determine the rotational period of the planet. So here you have part of the thing. So here you have, here is Jupiter here, and the position of Io is this angle here. Is what is called the Io phase, and we start counting from what is called the superior geocentric conjunction. So the Earth is located around here. So when Jupiter passed behind the planet, we start counting here. That's 90 degrees, 180, and so on. And the CML is pretty much the position of the planet. That's what determines the CML. So if you plot the same here, you can see that you get the emission for several configurations in the Io and the CML. So that means that for a given position of Io and a position of the planet, you get more probabilities of detecting the emission. The emission is probably not always there when you are pointing the antenna, but when you reach this kind of configuration here, this one here, or this one, those are called the Io sources. So that's the Io B, A, and C, which are well known. There are others that are probably less, the probability is less than some of these sources here. So what happened here regarding the emission is that you have the planet here, and the planet rotates in about 10 hours. And Io, one of the satellites here, and you can see it around here on the right side there, that's Io, is inside of the magnetic field there. But Io rotates much smaller, so it has around 42 hours to go around the planet. So that means that the magnetic field of the planet is sweeping past Io and generate what is called alpha waves. And those alpha waves will propagate in what is called the Io flux tube. So Io is somewhere here, and the magnetic field connecting Io to the planet is called the Io flux tube. And the electrons spiral there towards the planet. Some of them will hit the atmosphere. Some of them began spiraling in the opposite direction. And those are the ones that actually emit the emission. And you can see part of the auroral emission, and that one actually is caused by Io. So let me show you in more detail here, part of the same. So here you have the magnetic field connecting Io with the planet. And the emission is emitted in like a hollow cone. So when the cone, part of the wall of the cone is pointing toward the Earth, there is when we can receive the emission. When the other part of the cone is pointing toward the Earth, we have more probability of detecting the emission. So here you can see a couple of interesting things. So part of the electrons that are going spiraling and hit the atmosphere of the planet, they cause some kind of hot spot there. And those are called the footprint of the Io flux tube. So in the case of Io, it's there, but some of the other satellites like Ganymede and Europa, also have the same spot there. They are inside of the magnetic field, so they accelerate the electrons also, and the electrons will hit the atmosphere and cause that kind of hot spot there. Regarding the type of emission that you can listen, if you are listening to the emission at any frequency there, let's say 18 megahertz, there are two types of emission. One of them are called the L bursts or long bursts. You hear them like waves crashing in the shore there. So it's like a white noise that increases and decreases the intensity there, and that's all. There are others called the S-bursts, which are the short bursts. And those are probably described as pebbles on a thin roof, hitting the roof there. And so they are very short. And those are very interesting because it's something that we study in detail. And there is another kind of emission. It's called narrow band emission, which is something that in frequency is very narrow. And I'll show you part of the L burst here in a little bit. So here you have part of the spectrogram, which I recorded there using the TP antennas. So what you can see here, the background is coming from the galaxy, this noise coming from the galaxy. The galaxy is pretty strong at low frequencies. On top of that, you can see Jupiter emission, and this is what you can see here in the lower panel also. I recorded that. Probably some of you may recognize Hewlett-Packard spectrum analyzer, the 141T. I can see a few of them in the Hamcation in Orlando. They are still selling some of those things. So I recorded that using that one and recorded that on magnetic cartridge, DAT tapes, and then played them back and processed that with the audio analyzer in order to plot some of these things, and I digitized part of that one. So this is what you can see from what is called the L burst. They are very wide in band. You can see here that this goes from 16 to 30 megahertz or so. The scale is inverted here. At that time, we were using this inverted scale. So they can cover many megahertz there, the emission. So whatever you are, if you have any receiver there at any of these frequencies, you are receiving the emission. So it's not that you cover the narrow band, it's very wide band. All right, so let's continue a little bit more with another project that we started here probably in the around 1900 or so. And that is the Radio JOVE project. And the Radio JOVE project is kind of interesting, and we are still working with that project. I'll describe some of the things that we are doing there. The project was, the basic idea started here and then moved to Goddard Space Flight Center, the NASA Center in Virginia. And then we'll started from there because they got some money there, and the thing began growing. The idea of the project is that, okay, you can receive the Jupiter emission with using very simple antennas. And so it would be interesting to engage some of the high school and college students and the general public so that they can build a receiver or purchase a receiver and do that. Or if anybody has a short wavelength receiver, all that you can do is disable the AGC so that you can get the emission there. So here you have the website. So we began with the project with the receiver and the antenna at 20.1 megahertz there. So anywhere between 18, 22 megahertz is okay, but we finally decided around 20 megahertz, a little bit beyond the WWV, so that we didn't interfere with we didn't get the interference from WWV. So the basic idea is to use that kind of things and get people interested in radio astronomy. And like I said, the Jovian decametric emission is so strong, so you can receive that with very simple antennas and very simple receivers. And that's the only planetary radio emission that we can detect here on the Earth, the low frequency emission. Saturn and the rest of the big planet also emit low frequency emission, but the emission is below something like 1.3 megahertz. So the ionosphere doesn't allow to propagate the low frequency. So nobody has been able to detect Saturn emission from ground-based antennas here. Only Jupiter is the only one. So on top of that, we can observe the low frequency emission from the sun and also the galactic background, which is pretty strong at low frequency. And that's the one that when you turn on the receiver, you just disconnect the antenna and put it back. That's the increase on the noise that you hear when you put the antenna back. So here is the antenna. It's a couple of half wavelength dipoles there. And they are cut to about 20.1 megahertz there. So you have one dipole here, another one here. And so you connect the two lines here with the power combiner. And from there, you go to the receiver. If you do that and you don't add what is called a phasing cable there, the antenna is pointing straight up, the beam of the antenna. In order to point that one towards the declination of Jupiter, you may have to add a phasing cable there. And so we do that all the time. We have different phasing cable depending on the declination where the planet is. And we just wait for the planet to cross in front of the antenna. The antenna has a pretty wide beam, and here you have part of the wing. So if you, this was produced by the EasyNet, probably you are familiar with the software there. So this one is the diagram. If you connect both dipoles in phase there with the same length of cable, then you get this diagram that is pointing straight up. If you add the phasing cable, you can switch a little bit the beam. And if you put it out of phase, so you connect half a wavelength between one dipole and the other, you get these two lobes there. Sometimes we use that one if the planet's a little bit too farther away from the zenith, we use that one there. You can recognize here that the lobes are the same as this one here. This one should be a little bit lower around here because you split the big lobe in two, so the gain is a little bit smaller there. So here you have part of the antenna and the receiver. Here we have one of the members of the Radio JOVE soldering part of the same, and here you have the receiver. The receiver is kind of small. And here is Chuck Higgins, one of the members of the Radio JOVE, setting up the antenna with some of the students. So here you have one dipole and the other dipole, and then you connect the things to the center and go to the receiver. So that's pretty much very simple. Here you can see a few examples of what you can get using the Radio JOVE antenna and receiver. So here you have Jupiter. Those are all the deflections that you can see here are Jupiter. The deflection that you can see here in the background, that's the galactic background. So Jupiter's emission is mounted on the galactic background there. And here you can see an example of the sun. So you can see the small deflection due to the galactic background here. And when you get the sun goes normally pretty high. It's much stronger than Jupiter. And then it goes down. The shape there is called the shark fin, like kind of shark. That's pretty much characteristic of the emission from the sun. And here you can see the galactic background. If you record that for several hours, you can see a lot of interference. That here and here is interference. But during the nighttime, you can receive Jupiter there, and you can receive the galactic background there. That's when our galaxy passes right in from the center of the galaxy. I mean, the equator of the galaxy pass in front of the beam of the antenna. You get more deflection there. So that's another one there. So that's another of the members that was able to record that. We do that all the time. So let me tell you a little bit about a new system that we mounted at the Optical Observatory in Rosemary Hill. So the Optical Observatory is near Bronson, about 6 miles from Bronson. And since they began destroying all the things there at the Radio Observatory, we finally shut down and we moved part of the equipment there. So we put another system there. And that is part of what it used to be the Radio JOVE, but it's another group that is connected with Radio JOVE. It's called the SUG group. That means spectrograph user group. And we use a different type of antenna. It's called the TFD, or terminated folded dipole there. And we normally have 4 elements there. I'll show you that in a little bit. And we can separate the right hand and left hand polarized emission from Jupiter. The antenna itself was designed by Dept. He's a radio amateur. He lives in High Spring. He designed the antenna and all the system there. And that is the one that we are using. We have several groups already working and using that one. The one in Rosemary Hill is one of them. The sweeping spectrograph was designed by Dick Flang, which is another radio amateur, and Jim Sky. Dick is the one that designed all the electronic. Jim Sky do the things with programming of the spectrograph there. And so the antenna cores range between 18 and 30 megahertz or so. It can go back down to 15 megahertz or so, but you lose a little bit of sensitivity there. And of course, it can detect the sun, the galactic background, Jupiter, and things like that. So at the present, some of the groups that form the SUG group are beginning to use SDR receivers also. So they can cover probably around 6 or 8 megahertz there. So they connect that one directly to the antenna also. I just got one of the SDR receiver, and I had to start experimenting with that. Some of the locations of some of the stations that are connected with the SUG group are one of them in Rosemary Hill near Bronson, another one in Alachua, another one in High Spring, another one in Tennessee, another one in New Mexico, another one in Pennsylvania, and finally another one in Georgia. So we have all these stations there. Normally they are observing 24 hours a day, and we exchange data there. So part of this group is making plan to observe the total eclipse in 2024. We did observe during I think there was 2017, this total solar eclipse, and we still have part of the data, and we are trying to work with the data. I actually moved my antenna there to South Carolina, to Summerville near Charleston, and try to observe from there. Bad luck is that a couple of hours before the eclipse, we have a thunderstorm there, and the thunderstorm lasted for several hours, so we missed to see the eclipse, and it was full of interference from lighting, so I couldn't rescue any data from the observation. Here is the element there. That's the element for the TFD. So I'm not sure if you can see that one. Is mounted on 2 poles. That's about 9 feet or so from the ground. And you have the central part here, which I'll show you in details. And from there you go with the coaxial cable to the rest of the network there to connect all the things. And let me show you here in more details, and I can show you part of that. So you have 4 elements here like that. And so you have the north is in this direction. So you connect the one on the east and the west through a power combiner. And then the north and south, you connect with other power combiner, but you have to add one of the phasing cables there so that if you are receiving the emission at an angle there, because Jupiter is different angle, you can delay the emission in one dipole, and then before they can connect in phase there, you have to add a phasing cable. In other words, you are switching the beam of the antenna towards Jupiter. And we add a couple of things here that are source suppressor, so that this thing is like a 90 degrees hybrid. So you connect the signal coming from the north-south and east-west here, and then you separate the left-hand and right-hand emission from there. So that's all of this is in the field. And here you can see part of that one. So here you can see the central part of the antenna. Here is one of the coaxial cable that comes to the central part. And in the central part, you have the power splitter, you have the 90 degrees hybrid, and the phasing cables also. So using that kind of configuration, you can separate the right hand and left hand emission. So here you have part of that one. This is a balun. It's connect the input of the antenna, which has a high impedance, about 800 ohms, so that on the other end, you get something like 50 ohms, and that's the one that you connect with the rest of the things there. And it has a termination receiver resistor here at the top. So that's the antenna. And here you can see part of the emission. Here you can see part of the equator of the galaxy passing in front of the antenna. So this happened during the night when if you begin observing before midnight, you get a lot of interference there, and you can see many things there. I think this part here is part of the CV station that you can get there. After midnight, the interference goes down, so you can see part of the emission coming from the galaxy reach like a maximum there, and then goes down when the equator of the antenna pass in front of the antenna and move on the other side. So you have something like 20 hours of observation here. All right, here you have some of the emission from Jupiter that was detected using the system there in Rosemary Hill. So the spectrograph there goes from about 15 to 30 megahertz or so. And this is the emission there. So this panel here, the upper one is the right-hand polarization, and the lower one is the left-hand polarization, different polarization. The time here is in universal time. So this is pretty much during the night. And this emission is coming from the IOA source. The IOA source and the B source seems to be located in the North Jovian hemisphere. And in the southern hemisphere, you have another source emitting there, or another cone there. So the one located in the North hemisphere emits right-hand polarized emission. The one in the southern hemisphere, left-hand polarized emission. So normally you get both of them, but a little bit stronger in one of them, especially with the IOA source. Here you have the IOC source. This is supposed to be located in the southern hemisphere of Jupiter. So the emission is stronger here in the left hand and almost disappear here in the right hand. So that was part of my test with the antenna to make sure that it was working there. That was around 2018 or so when I did that. All right, let me tell you a little bit about observing pulsars, and that is pretty interesting. Pulsars is a very compact object. It's a neutron star which has a very strong magnetic field and rotate pretty fast. It rotates about once per second or once a few milliseconds. That is a pulsar. And so that was part of my thesis there. And so I began using the big antenna in the Radio Observatory here in Florida. And that is the 640 dipole there. The antenna is composed of half wavelength element, but they are separated by about 0.6 wavelength or so. So the beam that produces there is about 2.5 degrees wide in east north-south and 6 degrees in east-west or so. So you can observe the pulsar whenever the pulsar is in the beam. But the system produces multiple beams. So it produces, if you have the meridian, produces 8 beams to the east and 8 beams to the west. So you can go from one beam to the other and switch from one beam to the other and begin recording the signal coming from pulsars. And I use also the 45 megahertz antenna in Chile. So I had to go there, spend a few years and use this antenna. This antenna is at 45 megahertz, a little bit higher in frequency, and is 528 dipoles there. They are full wavelength dipoles there. And the antenna is pretty effective there. So the antenna itself covers a little bit more than 10,000 square meters, but the effective area of the antenna is pretty close to the geometric area of the antenna, very, very effective antenna. So the size of the beam there between half wave, the half of the beam there, half power is about 2.4 by 6.6 or so. Even at this frequency, the beam is not very narrow, it's several degrees or so. And so here is part of what I got, part of that. I got many observations. I cannot show you all of them because that will take a long time to do that. But this is what I came finally after combining all the data, especially at 45 megahertz. The signal is a little bit stronger from pulsars at 45 megahertz. So here you can see a list of the pulsars that I was able to observe. Here you can see part of the profile around here. And you can do that by integrating in period. What you do there, so if you are observing there, you have a long list of digital values there. But if you go there by one period, so you have one period, one pulse is there, but it's buried in the noise, so you cannot see it there. And you get the next period and the next period. So what you do there, you take one period, you average that on top of the other one, take the next one, average on top of the other. And so that will reduce the noise outside of the pulse, but the pulse itself begin growing there. And so that's what you get, that kind of things. And here you have the intensity in a standard deviation. So you compute the noise here, you compute the standard deviation outside of the pulse, and then you measure how high is the pulse in a standard deviation from the noise outside of the pulse. So here you have some of them. but you can see that you had to integrate over many periods there. I wasn't able to see any pulse there, except for one occasion in which I was able to see one individual pulse. You had to integrate for probably 300, 400 pulses there, stacked one on top of the other, before you can see some of that. So here I try to stack most of the observations so you can see that I was able to use a few thousand pulses there in order to produce this kind of things there. But you need a big antenna in order to do that. So here you have another part of the thing that I did. So here is, if you are observing in kind of wide band there, like I did here, I recorded that using an Ampex 600. That's a magnetic tape recorder. It's a big thing there, and the reels are kind of big. And I recorded that and then played them back here and using a spectrum analyzer, Cycor spectrum analyzer, it's a 200 channel. And you can see the pulse here. The pulse is sweeping in frequency. It goes from high to low frequency. That's characteristic of a pulsar. And the reason for that is that in the interstellar medium, you have electrons there. And that produces a dispersion. So high frequencies will arrive first and low frequencies a little bit later. So you can see the pulse here. And what I did in order to come up with this profile here is to begin cutting there each one of the sweep of the spectrum analyzer and then switching the things to put them together and finally end up with the pulse here. So you can see that the pulse is not just one single thing, as I was showing in the other one. I gained a lot of time resolution here, and the pulse is actually two pulses inside of the big pulse there. So let's switch to something else. Well, when we lost the access to both of the big arrays in Chile and here, I couldn't continue doing any more pulsars observation because we need big antennas in order to do that. So let's switch to a couple of other things that you may be interested. Probably you remember that the Arecibo telescope is no more. So the Arecibo telescope was damaged by a hurricane that was about 2 or 3 years ago that it hit Puerto Rico, and part of the cables here were damaged by the hurricane there. And they were thinking to actually repair part of that one. And then part of the cables begin failing there and cutting part of the thing here. And they were not sure if they can repair that. So they contracted with the engineering company to evaluate the damage there. And the conclusion from the company is that it was too risky to do any repairs there because most of the cables, especially some of the things that hold the cables here on top of the big pole, were beginning to come apart there. So the National Science Foundation, which was funding the project there, decided that it cannot be repaired and they had to take it down. Before they did that, and before they began working on that, on December 1st, the antenna came down. What came down was the central part where you have part of the receiver and part of the cable that come, because this is a radar thing. So all the thing that you have here, part of the wires here failed and the whole thing came down, and probably you can see the big damage there. So it was damaged without any possibility of doing any repairs there. So National Science Foundation decided that that's it. It had to be taken down completely. And but they have another one. So they have another project there. And it was a group of about 70 radio astronomers, which around March of this year came up with what is called a white paper, in which they proposed to rebuild a big antenna there, but in a different way. So they are not going to rebuild one single dish there. They are going to have smaller dishes here, and they are planning to have more than 1,000 parabolic dishes there in a plane there, covering about 300 meters or so around here. And they are still thinking, because the white paper just gave a few basic ideas on what they need to do there, but it's not the final project yet. If they come up with the final project, they have to go for funding to NSF. Let's see if they approve that. But some of the small dishes there, which can be much smaller, you can tilt them there, and so you can reach much bigger area of the sky. With the old dish, you have the the dish there, and it's like a spherical dish, and you can move a little bit the things around there, and that will change a little bit how far you can go from there. But you are pretty much tied to a few degrees around the zenith there. But using this configuration, and they are still thinking to break down some of the group of small dishes there so that they can tilt the things and reach a bigger part of the sky there. So according to that, they can probably reach about 2.5 times bigger coverage in the sky. And also they can reach much higher frequency there. So they can go something like 60 or megahertz or so, all the way to a few gigahertz, all the range there. So they are planning to do that, and they are planning to do many interesting things. Here is part of the science plan there. They can do more planetary radar there. So they were using the dish there to detect and characterize and compute the orbit of near Earth orbit asteroid, or what they call PHAs. Those are asteroids that will cross the orbit of the Earth. Potentially they can collide with the orbit of the Earth also. And so they were using that, and actually they were getting images of the orbit of the NEOS or PHA, and also compute the orbit. So that's pretty much. They call planetary defense there because one of them can hit the Earth and have a catastrophic event. And they can do a lot of things here. And one of the things that they plan to do is make some advances in space and atmospheric science, space weather and things like that. And they can use timing pulsars to detect gravitational waves, which is pretty interesting application. So they have many interesting. The white paper is about 80-page long, and it lists a lot of interesting things there that you can do if you rebuild and build a new observatory. Couple of more things here. The ALMA, probably you are familiar with the ALMA. This is probably the best radio telescope in the world right now. It's located in Chile at a very high altitude. So the altitude is about 16,000 feet or so, about 5,000 meters or so. And you can see where it's located. It's pretty close to the highest part there in the Altiplano between Chile and Bolivia. And so the antenna there is composed of 16 small antennas, and they have a diameter between 7 and 12 meters or so. The whole observatory the antennas, the equipment, and the operation is being financed by the USA through the National Science Foundation and the National Radio Astronomy Observatory. And there are other countries that are contributing to that. Japan, Canada, Taiwan, Korea, and Chile are contributing to that kind of things. The kind of science that you can do there is pretty amazing. Probably you hear something regarding that. They have been able to image protoplanetary disks. So you have the star at the center, and part of the mass they are going around the star that will form planet there. And they have been able, they have enough resolution so that they can actually picture the protoplanetary disk and how planets may be forming around the protoplanetary disk. I don't know if you heard about the detection of phosphine in the atmosphere of Venus. Phosphine is one of the molecules that are associated with life. Normally cannot be produced by just normal chemistry in an atmosphere, except that if there is life. And that is considered one of the interesting things to do regarding exoplanets also, trying to detect phosphine in exoplanets. Using the ALMA, they think they have detected phosphine in the atmosphere of Venus, which gives the idea that is there any type of life there in the atmosphere. That is still is part of the research, so they are not claiming that they detected life. They detected the molecule there, phosphine, that some other people are observing and reanalyzing part of the thing. Some of them think that what they think is a detection of phosphine is probably part of the way that they analyze the data. So very interesting there. And very interesting that the antennas are so high there, so the way to operate the antenna, they have a few things here to operate the antennas, but at 500 meters, pretty much you have to use oxygen there to do that. But the operation center is much lower. It's probably around 3,000 meters in San Pedro Atacama. That's another small town, much lower than that. And finally, the FAST radio telescope in China, which is pretty big, bigger than what it used to be at Arecibo. So the diameter there is about 500 meters or so. And apparently they can work between 70 megahertz and 3 gigahertz or so. They are trying to do a lot of science there. One of them is to detect what is called the fast repeating bursts. Those are things probably associated with neutron stars or black holes that collide and emit a lot of emission. And they have been able to detect a few using other radio telescopes, but that's part of the program using the observatory there in China, the FAST. Pulsar timing also, which is very interesting because if you're receiving the signal for pulsars, the period there is very interesting because the period remains there. There is a little bit of drift in the period there, but not much. And if you have any gravitational wave between the pulsars and the Earth, it will distort the space-time there, so the period there will change. And so they are thinking to do that, and they are thinking to do the same thing with Arecibo. And they want to be part of the SETI program, Search for Extraterrestrial Intelligence, and they will be part of the VLVI, the Very Long Base Interferometer. VLVI was used in order to detect the shadow of a black hole in a galaxy, M87 there. So they will be part of that one there. They will continue doing that using other galaxies. just for comparison here, you have what it used to be the old Arecibo telescope, about 300 meters. You had the fast, about 500 meters or so. And just for comparison, we have the Ratan 600, that's a Russian telescope. The Russian telescope is not a dish, it's a series of telescopes in like a round location there. So they gain a lot of resolution regarding angle there using all the separation there. But one of the interesting things is that the FAST telescope is not a radar telescope. It's just passive radio telescope there. So they have part of the receiver here, and they can move the things a little bit so they can have access to some part of the sky, but they are a little bit restricted because they cannot move the whole disk. And that is something that they may be able to do with the new Arecibo telescope if they are able to do that. All right, I think I went a little bit more than I want to go, so let's finish with that one here.
Okay.
All right.
Francisco, I appreciate that very much. Highly interesting. And I made a lot of notes here. I'm going to follow up on to answer some of my curiosity. One thing, I don't know if you answer this one right off the top of your head, but the 2024 total eclipse, do you know where the shadow is supposed to pass across the Earth?
Right. If you want, I can show you there. But I can send you the link or the image. Yeah, it's going to pass. It begins around Mexico there. I think it goes around New Mexico and goes through the middle there and exit in the east part of Canada there. So it covers a good part of the central part of the US. And
so we get in Florida, we won't see a total, we'll see a partial maybe?
Right, from Florida, we see a partial solar eclipse.
Okay,
so
cool.
What we were planning is I may, if I can find a place there, I may take part of my antennas and set it up there in the middle of the totality path, which is not more than probably 80 kilometers or so. So you have to be within there. And some of the other people that belong to the SUG, the group there, some of them will be observing from wherever they have the station, but I can hear that a few of them were thinking also to move there and be in the path of totality and see where you can observe even outside of that. What we were trying to observe is the galactic background emission. So you are pointing the antenna to the galaxy there, and you are receiving this signal that is pretty much like a flat thing. But when totality passes in front of that part of the ionosphere, it will reduce the ionization there. So you are expecting to see a little bit of the increase in the galactic background because you lose a little bit of the absorption in the ionosphere. That's the basic idea. Many radio amateurs are using actually reflection of other stations there to see how behave with the ionosphere. And I think they are doing pretty good job regarding that. So they may be observing the same thing.
I'll have to look into what the plans are with respect to maybe ham radio observation of that and get myself ready if I can. I think we got a question from Paul. Eugenia? Yeah.
Hi, Francisco. My name's Paul. So, the radio wave, astronomy is really advanced, astrophysics, just like the regular telescope did with the days, going back. And some of the advances like, that you mentioned and those like the cosmic microwave background are pretty amazing. Recently, though, there's been a lot of excitement by another type of, gravitational wave astronomy. And I'm very familiar with the laser interferometry of the detection of the gravitational waves. But what caught my attention was when they talk about high frequency and low frequency, right? These are relative terms, right? They mentioned that another way in which they're measuring gravitational waves is through using radio telescopes for low frequency. And what I found striking was low frequency was nanohertz, right? 10 to the minus 9 hertz.
Yeah.
That I couldn't wrap my head around. I'm wondering if I'm just wondering if you know anything about that at all, or?
I saw something there, but I didn't actually get the chance to read the article that, yeah, they are thinking to do something like that, but I'm not sure exactly what they can detect there. My guess is that they can detect some changes at very low frequency that may be caused by the passing of a gravitational wave. But I don't know more details regarding that, but I'll be very happy if I can get to read an article there and see how they want to do that. So no, I don't have much to comment regarding that because I haven't read the article.
Mm-hmm.
Right. No, the other thing that I mentioned here that they are planning to do is do pulsar timing. And so if they are doing that, pulsars, the repeating period is very stable. There is a small change there because you have the neutron star rotating there, so it's losing energy. So it's begin rotating smaller and smaller. But you can predict that one, the decrease in the rotational period there. And if they are observing that, and you have a gravitational wave passing between the pulsars or several pulsars and the observer, that will distort the space there. And so that will change the periodicity between the pulses there. And that seems to me like a pretty interesting application of what they need to do there.
Okay. All right. Well, thank you.
I'm not sure if anybody has any questions.
I was muted, I'm sorry. We had a question from Todd Clark. If he's still here, maybe took a break, but anyway, here's the question. Will there be less of a chance for observing signals from Jupiter during the upcoming solar cycle?
Yeah, that's part of the interesting things. I couldn't go into a lot of details there, but the probabilities of detecting the Jovian emission seems to be connected with a couple of things. And one of that may be connected with the solar cycle. The other one is regarding the orientation of the Earth regarding the planet. So you have the planet here and you have the cone of radiation, but the Earth is moving away or inside of the cone of radiation during a period of about 12 years or so. And that pretty much coincides with the same periodicity in which the solar cycle is changing. And that is something that we are still trying to take a look to disentangle the two periods. And the probabilities of detecting the emission changes there. And it changes, we don't know exactly if we know that it may change with the position of the Earth going in and out of the cone of emission there, but it may be related also to the case of Jupiter. And the amount of energy receiving from the sun during a minimum of solar radiation, it received less energy there. During a maximum, it received more energy. So it may be connected to that too. So the answer is there might be a connection between that. And we know that right now that the probability of detecting the emission changes. So it's higher normally during a minimum of solar emission and less during a maximum of the solar sunspot. But we haven't been able to disentangle the two things yet.
Well, maybe the next cycle will help us do that.
Right.
Anybody have
So
any
if we
other
continue observing during several cycles, we can see if we can disentangle the two things, because they are not exactly. So at some point they will be out of phase, and that will be something interesting.
Hey, very good. Any other questions? Well, thank you very much, Francisco. This was very enlightening. It also made me realize it's a pretty complex subject. I don't know if I would have survived the other astronomy courses than the one I took, especially getting into the more advanced science like you do. But it has piqued my interest. I'm going to follow up on that Radio JOVE and read more about that. And my only parting comment here is when they put up a new Arecibo telescope, I sure hope they try another moon bounce with ham radio. They did that about 10 years ago or whenever it was. I missed my chance. I had my antenna set up, but it was the wrong circular polarization the whole time, and I couldn't quite hear them. So I want another chance.
Yeah, that will be interesting to see.
Yeah, we could.
The reflection of one of the Arecibo pulses there in our antennas. Yeah.
Well, thanks again, Francisco, and everyone. It's been a very enjoyable presentation tonight. And if you get up in our neighborhood on Thursday, the first Thursday of every month, we have our club meeting at 7 p.m. Hopefully we'll be back together in our building at the Red Cross one of these days before long, but I guess it'll be not till later this summer. But pleasure having you here, and thank you again.
Yes, thank you. And if you have any questions or any links that you let me know, and I can send you links, especially to the Radio JOVE and the thing that we are doing right now with the SUG group.
Okay. Thanks.
All right.
Good night.
Yeah, good night.
Thank you very much.
You're welcome.
Thank you.
Thanks.